Hey, Algebra 2 honor students, this is going to be Unit 6, Day 3. And for Day 3, we're going to continue our discussion of factoring by grouping. We started that a little bit at the end of Day 2's lesson. So as we go through the notes, this is in your packet starting on page 8. You'll find that there's a bunch of examples that I'm suggesting that you know how to do already. So I've asked you to try number 1, try number 4. You'll see try number 5 down here. So anytime it says try it, these are examples that I'll expect you to have filled in your notes already before coming to class tomorrow. So if you want to hit pause right away, try 1, 4, and 5, go for it. But otherwise, I'm going to jump right into number 2 and start showing you the factorization for something like that. So for number 2, x cubed minus x, and then minus x squared plus 1. Whenever we see 4 or more terms, we want to consider that maybe this is factoring by grouping. And by the way, even though that's the title of today's lesson, that it's factoring by grouping, not every example will involve grouping. So 4 and 5, I wouldn't expect you to use a grouping technique with either of those. Those are kind of looking back to what we've done in days 1 and 2. But taking a look at number 2 here, 4 terms, yeah, I mean, I think our go-to so far at least has been let's group the first 2, let's group the second 2, and let's see what happens when I do that. So from the first group, if I take out an x, that leaves me with x squared minus 1. All right, take out the GCF from that first group. From the second group, whatever I take out, I want to hopefully be left with x squared minus 1. And we can accomplish that if you take out a negative 1 GCF. And that's a little tough to recognize at times, but if you factor negative 1 from those two terms, you're left with positive x squared, and then taking negative 1 from here leaves you with negative 1. So now if this is one group and this is another whole group, x squared minus 1 is in common, so take that out as a GCF. That leaves you with x from the first group minus 1 from the second group. So although this is now factored, right, we've written it as a product, you have to be cautious that we have to continue factoring if it's not completely factored yet. So x squared minus 1, that would break down to difference of perfect squares, x plus 1 times x minus 1. And then also bring down the x minus 1 over here. This is a perfectly acceptable way of writing your final answer for number 2. It is now completely factored. But if you want to be fancy, you could write this as x plus 1 times the quantity x minus 1 squared, right? If you have two binomials that are the same, you can write it as that quantity squared. Perfect. All right, so that one is a little bit weird. By the way, if you had rearranged the order, what I mean by that is put the negative x squared first and then the negative x, kind of switch the inside order, you would still factor it in the same way. So sometimes rearranging the terms is an okay step to do if you notice a different grouping that's possible. Taking a look at number 3. If you look at all 4 of these terms, before you even get to grouping the first 2 and the last 2, you might have noticed something unique about this, is that for all 4 of these terms, there's a GCF of 2. And that's not super common to see, but you can take out a 2 from everything. So that leaves you with 2x cubed plus x squared minus 6x minus 3. So taking out a GCF is not necessarily good enough to say, all right, cool, we're done with the process. You now are going to use a grouping technique on the inside. And let's see what happens when I group the first 2 and the second 2. Okay, all along the way, by the way, you want to keep on bringing down that 2. So maybe I'll just kind of like factor the inside and put it in this big bracket here. All right, so from the first group, you can take out an x squared, and that leaves you with 2x and a plus 1 left over. From the second group, remember the whole goal here is if I take out a GCF, I want to be left with 2x plus 1. And we can accomplish that if we take out negative 3. Taking out negative 3 leaves you with 2x plus 1. So now that I have this as one group and this is a second group, they both have 2x plus 1 in common. So you can take out 2x plus 1 on the outside. And then after doing that, I'm left with x squared from the first group minus 3 from the second group. Okay, so the factoring on the inside would be, again, 2x plus 1 here, and then x squared minus 3. And that's essentially the correct answer. You don't really need these big brackets around this anymore. You can drop those brackets at this point and just have the 2 hanging out on the outside. You don't have to write that in an additional step, but if you have an answer that looks like this, that is a correct final answer. What if I didn't recognize that 2 is the GCF to start? Because I think that's pretty common. We see 4 terms and we're just like, all right, 2 and 2, let's go. What would have happened in the end is that your 2 factors that you have here, one of them would have had a GCF of 2. So not a big deal, but in the last step there, I guess, if you have 2 factors, but they're not completely factored, then take out that GCF of 2 and kind of go from there. You'll notice that number 6 says skip altogether. So there's nothing going on special with number 6. You don't have to try this one. I would like you to at some point try these 3 on the first page, page 8. Let's go on to number 7. Number 7 is a squared minus 10a plus 25 minus 9b squared. All right, our default so far has been first 2, last 2. And when I group the first 2, there is a GCF of a, so that leaves me with a minus 10. And when I group the second 2, there's no GCF, so we're getting a little nervous maybe about this grouping here. Now, even though there's no GCF, isn't it factorable? Isn't it difference of 2 perfect squares? So that would be 5 minus 3b and 5 plus 3b. Okay, so looking at this result, if that's what we have from the factoring of those 2 groups, what we can see is that these 2 groups have nothing in common. Even though this wasn't a GCF case, I still factored it, but now this and this, they really have nothing going in common there. So because of that, even though I've done some factoring, this is not a factored expression. We have things separated by this plus sign here. So my initial attempt at factoring this is incorrect. That's not what I want you to write in the end. So I guess I should have used pencil for this, shouldn't I have? Okay, but that's all right. I'll still have plenty of room to do this. So if I go back to the original, it turns out that grouping 2 terms and 2 terms, even if I do some rearranging of the terms, it's not the correct pattern. In fact, look at over at number 10. How am I going to do 2 and 2 when there's 6 terms altogether? That's pretty weird. So there are other grouping techniques that we can attempt. And the other groupings that we're going to wind up seeing are 3 by 1. So group 3 terms together, leave 1 off to the side. Maybe it would be 1 by 3. These kind of seem the same, but they do look a little bit different. And then if you have a total of 6 terms, 3 by 3 will be the common technique for that. So since I tried 2 by 2 and 2 by 2 didn't seem like a good option here, why don't we look at 3 and 1? When you use these techniques, by the way, 3 by 1, 1 by 3, and 3 by 3, they all eventually become the same thing. Eventually, each of these techniques become the difference of perfect squares, which seems a little odd. We didn't see that coming, but eventually, each one of these cases will break down to difference of perfect squares. Now that we know that, why do we like this last term, minus 9b squared, as my single standalone one term? Well, 9b squared is a perfect square, and it's being subtracted. So what am I hoping about this trinomial? I hope that it's a perfect square, meaning that it factors into the same binomial twice. So can I factor this into a binomial squared? The answer is sure. This would be a minus 5 times another a minus 5, which we're going to write as a minus 5 squared. So when I group those first 3 together, it becomes this perfect square, minus 9b squared, which is also a perfect square. And then, even though we've done some factoring here, we're not done. We now have to do the difference of perfect squares. So from there, think about taking the square root of each of these. You would get a minus 5 plus 3b, and then a minus 5 minus 3b. This is the final answer. It's going to take a little while to get used to this pattern and this technique here, right? When we do 3 and 1, how are we going to start recognizing that? If you have these perfect squares that are hanging out, maybe it's at the end, maybe it's at the beginning of the expression, and it would be a 1 by 3 case. That's how we're going to start maybe choosing 3 by 1 instead of 2 by 2, which didn't quite work out for us here. Okay, let's take a look at number 10 and see if we can use, if it's a 6-term expression, it's definitely going to be 3 by 3. So if I look at this grouping here, the first three and the second three, what I'm hoping is that eventually this will turn into difference of perfect squares. And in order to make that happen, to get difference of perfect squares, I want to factor this trinomial into a binomial squared, just like I did over here. Same thing with this trinomial. I'm hoping that it becomes a binomial squared and that we're taking the difference of those two things. To set the stage for that, something that's really critical to do here, when you're doing 3 by 3, your second group of 3, you have to factor out a negative from that group, because we want to eventually create this difference of two perfect squares. So when I take a negative from that whole group of 3, it becomes x squared plus 6x plus 9. All those signs change. Now that I have it written in this format, let's think about what this trinomial factors into. Y squared minus 16y plus 64. That's going to be y minus 8 times y minus 8, which is y minus 8 squared. Minus this quantity, x squared plus 6x plus 9, that would be x plus 3 times x plus 3, which is x plus 3 squared. And now that I have these written as perfect squares, and I'm taking the difference of those, if I think about taking the square root of each, it's going to start getting a little weird, guys, because I think what you'd want to do is if you need to, use a dummy variable here. Call this a squared minus b squared and think about how that factors. But then go back and replace those quantities for your dummy variables. I'm going to do it without dummy variables here, so hopefully you're okay that it's y minus 8 plus x minus 3. And then y minus 8 minus the quantity. Oops, that's supposed to be a plus still. So if we take about the square root of these, it's this plus x plus 3 and then that minus x plus 3. The double parentheses are kind of important, not as much in the first case, but in this case over here, that negative belongs to the binomial x plus 3. So if you want to drop those into parentheses, that's okay. In this case, it would be y plus x, and then actually combine like terms. Negative 8 and 3 is minus 5. But over here, when I drop the inner parentheses, you have to distribute that negative. So now this is y minus x. Negative 8 minus 3 is minus 11. So in factored form, this is what the final answer looks like for number 10. Definitely of a higher level of difficulty compared to some of the other grouping examples we've looked at. Let's take a look at number 8. And by the way, you can see number 11 is a try it, and my hint is dummy variable. All right, think about dummy variable for those two spots. For number 8, looking at this, could I try 2 and 2? Of course I can, but I'm seeing a lot of things that are perfect squares here. And when I see a lot of things that are perfect squares, I might start thinking that it's maybe 3 by 1 or maybe it's 1 by 3. In this scenario, if you look at this 2bx term, this sometimes happens where if you have a term that has two variables in it, b and x, it wants to hang out with the x squared and the b squared. And what I'm going to do to get this started is I'm going to actually just slide this in between x squared and b squared. So I'm going to write minus x squared plus 2bx minus b squared. And it turns out that if I group all 3 of these together and I leave this one alone, this is a good candidate for 1 by 3 grouping. Okay, the first term is a perfect square. And eventually when I factor this trinomial, that will also be a perfect square. Now, just like I did over here, remember when I wrote my second group of 3, I factored the negative from that group of 3? We have to do the same thing here to set the stage for 1 by 3 grouping. So I'm going to take a negative out from x squared, and then this middle term becomes minus 2bx. If I take a negative from here, now it's plus b squared. Okay, now we can go ahead and factor this into a squared minus the quantity something squared here. All right, if I think about how this factors, this is a little bit tough to factor when we have that double variable, but we're going to start seeing it come up in other examples. So if we think about this, the only things that multiply to x squared would be x times x. And the only things that are going to multiply to b squared are b times b. So how am I going to get that middle term of negative 2bx? By making this x minus b. And of course, if you were to check this with box method or FOIL, you'll get the same trinomial again. Okay. So this is a perfect square. It factors into x minus b squared. And now that I have it written this way, you can factor with difference of perfect squares. It's a perfect square minus another perfect square. So thinking about taking the square root of both of those, you would get a minus the quantity x minus b, and then a plus that quantity x minus b. It's important to have the parentheses here in that second location because this negative belongs to the binomial x minus b. It's really easy to lose sight of that. So if you distribute that negative in, you would get a minus x plus b. Over here, you don't really have to distribute a positive. You can just drop those parentheses and leave it as a plus x minus b. And now this is a factored expression. It's written as a product. But these take a little longer to get used to. So with a little bit more practice, I think we'll get there. Okay, you're going to try number 12, but let's talk about number 9. Number 9, the nice thing is that when it's 6 terms, it's going to be 3 by 3 factoring. And if I compare it to what we had in number 10, let's go ahead and group the first 3, and we'll group the last 3. It doesn't always work out that way. Sometimes you have to do some rearranging of terms. But hey, see this middle term with di in it? It wants to hang out with d squared and I squared. It's friends. And guess who gh wants to hang out with? G squared and h squared. I mean, I'd encourage you to make new friends, guys, but not in this scenario, not with factoring. They're very particular about their groupings. All right, so remember that before we go ahead and set this up to do difference of perfect squares, you really need to factor a negative from that second group of 3, just like I did in number 8, just like I did up there in number 10. So when I take out a negative, what does that leave me with? G squared plus 2gh plus h squared. Take a negative from all of those. Okay. By the way, I don't love the variable I just because we want to think I squared is -1, but that's not the case. So hopefully you're not going with that here. Okay, this is just a variable, not an imaginary unit. Okay. So what does this factor into? It would factor into d minus I squared. Right? D times d is the d squared, I times I, and the middle term of negative 2di is d minus I squared. Minus, what sign do I have to put in between g and h to get a positive 2gh in the middle? Well, better be plus. And if you do g plus h times g plus h, you're going to get that trinomial again. So now that we have difference of 2 perfect squares, we can do our factorization where we do d minus I plus g plus h, and then d minus I minus g minus h. Okay. In the first stage, I like having the double parentheses there, and you can drop those innermost parentheses by, just in that last case, distributing the negative to this binomial. So you get d minus I plus g plus h, no issues there. But in the last, d minus I minus g plus h. These tend to be factoring questions that are a little bit more challenging. So I am going through this quickly, but I promise we'll get more practice next time I see you in class. Okay, we got one more to try. 13, we're going to do that in class tomorrow. If you want to challenge yourself, I'll say to do 2 and 2. Okay, that's my hint for that one. So it's not 3 by 1, it's not 1 by 3, but it is a tough one to do 2 by 2 with even. You're going to try 14 and 16. 16 is really similar to what we just did with the double variables in number 9 over there. Okay, but you have to do a little bit of a rearranging. AC wants to hang out with a squared and c squared. The BD wants to hang out with b squared and d squared. So you have to do a little bit of rearranging there, but I do want you to try it. I think you guys can handle it. Let's go back up and try number 15. That's the last one I'm going to do with you. When I think about how we're going to group this, you can try the first 2 and the second 2. Here it would be difference of perfect squares. Here there's a GCF of, I guess, F in that case. But there's going to be nothing in common with those 2 groups. So what I'll tell you about number 15 is when you see a perfect square, like 9 out front, maybe we can start thinking that it's that 1 by 3 technique. And in fact, that would be a perfect square trinomial once I factor out that negative. It takes a little while to get used to this, but when you take out the negative, it becomes w squared plus 2wf plus f squared. So when you see that double variable, think about, hey, if there's a w squared and an f squared, does pairing that all up make it a perfect square to factor into? Because the three terms came second and they weren't the first three, you have to factor a negative from that whole group of three. So this becomes 9 minus the quantity w plus f squared, right? Because if the middle term is positive, I got to keep this positive here. And we're pretty close now. Think about taking the square root of each of these. So we get 3 minus w plus f, and then 3 plus w plus f. Distribute the negative here to get 3 minus w minus f. And then you can drop the parentheses over here to get 3 plus w plus f. Okay. There's a lot of practice coming up with these techniques on a grouping homework. So with some extended practice, I know you guys will get the hang of this, but if you're struggling at all to recognize some of these patterns, you'll let me know next time I see you in class. All right, have a great rest of the day. See you guys soon.